Across the deep quiet of the universe, there are events that simply refuse to make sense. Stars vanish without leaving debris. Signals appear with impossible precision and then go silent, and entire objects drift off course as if pulled by something we cannot see. These aren't theories, they are real observations that sit at the edge of what science can explain. Tonight, on The Galaxy Scientist, we drift toward these unsettling mysteries and trace the faint clues they leave behind, wondering gently what the universe is trying to tell us through its contradictions. If this quiet kind of curiosity feels right to you, a soft like and a quiet subscribe help others find their way here. Settle in now, and we'll step a little deeper into the unknown. Something unseen is tugging on our home in space, a quiet pull guiding our galaxy toward a region of sky so hidden that astronomers simply call it a zone of avoidance. We are not resting in the cosmos, we are drifting through it, carried along at about 455 meters per second, moved by a force we cannot see and do not yet understand. Between the scattered islands of galaxies, in the dark stretches of almost nothing, radio waves travel like thin, tired cries, crossing billions of years before they brush against our instruments. Far away, black holes that should be far too young to be so massive already feed on stars, swallowing their light without a trace. And all around you, almost everything that exists is not the matter you know. Close to 95% of reality is made from ingredients that do not fit into any catalog of normal substances. Astronomers live with these facts the way you live with the night, familiar and yet still a little unsettling. The more they stare into the sky, the more they realize how much of the universe lies beyond the edge of understanding. One of the first great puzzles began in the arms of spiral galaxies. Scientists measured how fast the stars at the edges circle their centers. By all the rules we rely on, stars far from the middle should move more slowly, the way distant planets move more gently around our star. If gravity were acting only on the visible matter, those outer stars should be loose, ready to drift away into the dark between galaxies. But they are not drifting. When astronomers traced their paths, they discovered that stars on the outskirts move at nearly the same speed as the stars closer in, as though an invisible weight were anchoring them in place. Galaxy after galaxy shows the same stubborn pattern. Something hidden is holding everything together, stopping the grand structure from flying apart. To give this unseen presence a name, astronomers call it dark matter. It is not dark in the way a shadow is dark, because it does not soak up light, it does not shine, and it does not reflect. It does not give off any kind of radiation our detectors can catch. And yet, by its gravity, by the subtle ways it bends light and shapes orbits, they can tell that it is there. Dark matter seems to make up a bit more than 1/4 of all the stuff in the universe. Roughly 27%. Ordinary matter, the kind that builds your skin, the air in your lungs, the ground beneath your feet, and the stars above you, counts for only about 5%. You, your world, and everything you recognize are a tiny, bright trace in a universe mostly woven from the invisible. It can help to imagine the cosmos as a vast spiderweb stretched across a dark room. The galaxies are the small beads of dew resting along its strands. Those threads themselves are made of dark matter, forming a hidden framework that gathers ordinary matter into the shapes we can see. Without this secret web, every galaxy would slowly loosen and unravel. Every star would wander away alone, and the sky would never have formed its graceful spirals and clusters. For decades, Scientists have tried to meet dark matter more directly. They have built delicate detectors, deep underground, shielding them from stray radiation, hoping that now and then a dark matter particle might nudge their instruments with the smallest whisper of a signal. They have searched for theoretical particles with gentle acronyms like weakly interacting massive particles, often shortened to WIMPs, and others called axions, spelled AXIONS. Time after time, the machines record only the usual background and no clear sign of a new kind of particle. Whatever is holding the universe together continues to act from behind a curtain. Some researchers have wondered if the problem is not a missing substance, but a misunderstanding of gravity itself. That perhaps the familiar laws change their behavior when distances stretch to galactic or cosmic scales. Yet every attempt to rewrite gravity introduces new mismatches somewhere else. The weight of the evidence still leans toward matter we cannot see. Dark matter seems to have been present when the first galaxies were nothing more than slight ripples in the early universe. Its gravity would have helped pull clouds of ordinary gas together, allowing stars to ignite and gather into the structures we observe today. Without that guiding pull, the cosmos might have remained a thin, uniform fog. No stars, no planets, no living worlds. You are moving inside this cosmic skeleton every moment of your life. Right now, your body is almost certainly passing through dark matter, the way a person walks through a faint mist. Millions of dark matter particles could be streaming through your hand in this very second. You feel no impact. Your nerves stay quiet. Our instruments, too, remain mostly silent. We know the structure is there only by its invisible strength. Astronomers estimate that, on average, there is about 5 times as much dark matter as regular matter in the universe. Imagine stepping into a crowded hall where 6 people are on the move, brushing past one another, but only one of them is visible to your eyes. You sense motion in the air, you hear footsteps and low voices, yet when you look around, you see almost no one. That is the kind of reality we live in on the larger scales. The unsettling thought is that dark matter may not be just one simple ingredient. It might be a whole family of particles and interactions, overlapping and subtle, operating in ways our current tools barely begin to touch. Each new telescope and each refined calculation brings more detail, but rather than closing the gap, it often sharpens the outline of our ignorance. We discover, again and again, that our picture of the universe is missing most of its paint. And even so, dark matter is only part of the strangeness. There is another player in this quiet drama, one that makes dark matter seem almost straightforward. When astronomers studied distant exploding stars in the late 1990s to track how the universe has been expanding, they expected to find a slow, graceful deceleration. Gravity, they thought, should be tugging on all the galaxies, gradually easing their outward rush. Instead, they discovered the opposite. The expansion is not slowing, it is speeding up. The fabric of space is stretching faster now than it was in the past, and the speed of that stretching is still increasing. Galaxies are being carried away from one another by a kind of cosmic push that no one had planned for. This discovery has been checked and rechecked using different methods, and it keeps holding true. To give a name to this unknown, scientists call it dark energy. In terms of sheer contribution to the universe, dark energy is vast. It appears to make up roughly 70% of all that exists. Quiet, yet overwhelming, it dominates the large-scale behavior of reality. And still, no one can say what it truly is. Every attempt to pin down its nature seems to clash with something else we know. Its existence alone sits awkwardly beside our best theories of physics. To feel how strange this is, Picture yourself tossing a ball gently up into the air. In your everyday world, gravity slows the ball, stops it for a heartbeat, then pulls it back. Now imagine a world where the ball, once thrown, begins to rise faster and faster, racing away from you as it climbs. That is something like what space itself is doing on the grandest scales. One way of describing dark energy is to say that it gives space a kind of negative pressure, pushing rather than pulling. The more space there is, the more room there is for this pushing to act. Unlike a gas that thins out as it expands, dark energy does not seem to dilute. Its influence grows with the size of the universe. Long ago, Albert Einstein included a term in his equations, the cosmological constant, to allow for a static universe. It behaved in a way that, in hindsight, resembles dark energy. He later dismissed this addition, calling it a blunder when evidence suggested the universe was expanding. Now, the sky itself hints that his extra term may have captured a real feature of reality, even if the story around it was different. Because of dark energy, the universe is not expected to gather itself back for a grand collapse. Instead of a big crunch, the picture that emerges is one of gradual thinning over unthinkably long stretches of time. Galaxies beyond our local group will be swept so far away and so quickly that their light will never cross the growing gulf. To any future observers, the universe will appear small and quiet, with only the nearby stars and galaxies visible in an otherwise empty darkness. This slow, cooling fate is sometimes called the Big Freeze. Yet some possibilities are harsher. Certain models suggest that dark energy might not remain steady. If its strength slowly increases, the acceleration of the universe could grow more and more extreme. First, it might pull apart clusters of galaxies, then individual galaxies themselves. Later, it could overpower the gravity-binding stars to their planets, and finally, even the forces that hold atoms together. In that scenario, often called the Big Rip, everything would eventually be torn into its smallest pieces, scattered across an ever-expanding emptiness. The universe would end not in a quiet fading, but in a kind of final, stretching disassembly. No one knows which path our universe is truly on. Dark energy could stay constant, it could grow stronger, or it might change in ways we do not yet know how to imagine. Some researchers suggest that dark energy is woven into space itself, a property of the vacuum. Others treat it as a new field, a gentle background filling all of reality. A few continue to question whether our equations for gravity remain accurate at the very largest scales. None of these ideas has settled the matter. For now, we live in a cosmos governed, on its widest stages, by a force we cannot point to, cannot predict with confidence, and certainly cannot turn off. It has been driving the acceleration of space for billions of years already. Even in this quiet moment, you are being carried outward, faster than you were when you first began listening. The expansion continues, the acceleration grows, and we are passengers without any way to touch the controls. All of this raises another soft, persistent question. If the universe is so dominated by invisible matter and invisible energy, how did the small portion we can see manage to survive at all? What happened to its mirror image? According to the laws of physics that describe the earliest moments after the event we call the Big Bang, creation should have produced equal amounts of matter and antimatter. These twin forms are deeply alike, but opposite in certain key properties. And there is a strict rule between them. When a particle of matter and its antimatter partner meet, they annihilate in a flash of pure energy. If the early universe had contained them in perfect balance, they should have destroyed each other almost completely. There should have been no leftovers, No stars, no galaxies, no planets, no living beings to listen and wonder. Yet the universe we see is built almost entirely from matter. Antimatter, apart from small amounts created in energetic processes, is largely missing. To picture how strange this is, imagine a vast room holding 1,000 people in red shirts and 1,000 people in blue shirts. You know that whenever red and blue touch, both vanish instantly. A moment comes when everyone starts moving, bumping into each other. You step outside, then return some time later. Almost all the people in blue have disappeared, but the people in red remain, filling the room. You would have to ask what subtle rule favored one color over the other. This imbalance is not a small side detail. It sits at the foundation of why anything exists. In huge particle accelerators, scientists smash particles together to recreate, for a fleeting instant, the conditions of the early universe. When they study what emerges from those collisions, they see matter and antimatter born in almost perfect pairs. The symmetry holds under their gaze, yet clearly, in the first moments after the Big Bang, something broke that symmetry. The difference did not need to be large. Calculations suggest that for every billion particles of antimatter, there may have been 1,000,001 particles of matter. That single extra grain of matter out of every billion became the seed for everything. All the gas that would form stars, all the stars that would forge heavier elements, all the dust that would assemble into planets, and eventually all of life itself. That quiet 1 in a billion advantage is the reason you can sit here and think. Scientists call this mystery baryon asymmetry, the imbalance between matter and antimatter. Some ideas propose that matter and antimatter decay in slightly different ways, that there are tiny asymmetries in how they transform into other particles. Those differences might have tipped the scales just enough in favor of matter. Experiments have indeed seen small mismatches in the behavior of certain particles, but so far, the size of those effects seems far too small to explain the overwhelming dominance of matter we observe. Others suggest a different possibility, that antimatter was not entirely destroyed, but retreated into regions of space far beyond what we can see. Perhaps somewhere, separated from us by vast distances, there are domains where antimatter gathers into stars and galaxies of its own. An antimatter galaxy would look almost exactly like a matter galaxy from far away. The light would shine in the same colors. The patterns would be familiar. Only when matter and antimatter meet do their differences appear. If this picture were true, there would have to be boundaries somewhere in the universe where regions of matter and regions of antimatter touch. Along those borders, annihilations would be constant and intense, producing floods of high-energy gamma radiation. Astronomers have searched the sky for such sharp, bright seams, listening for the telltale hiss of these collisions, written in light. So far, the universe has offered no such sign. They have not found any trace at all. Yet there is a quieter, darker possibility that lingers at the edge of all this. Some physicists suspect that, in the very first heartbeat of the universe after the Big Bang, the rules themselves may have been different. For a brief instant, shorter than any fraction of a second we can easily imagine, the laws of physics might have worn another shape. In that fleeting moment, the perfect balance between matter and antimatter could have cracked. Matter gained its tiny advantage. And then, as the universe cooled and expanded, the laws settled and locked into the form we know today. If that is true, you exist because the universe allowed itself a brief slip, an asymmetry that should not have happened. The fact that you can think and listen and wonder about this mystery is evidence that, once reality bent its own symmetry, and if it broke its own rules once, softly and almost invisibly, there is nothing in principle that guarantees it will never do so again. While we are still trying to understand that first imbalance, something stranger is calling to us across the void. In the early years of the 21st century, astronomers noticed a scream written in radio waves. In the year 2007, a burst of radio energy suddenly washed over Earth. It lasted for less than about 5/1000ths of a second. In that tiny sliver of time, it seemed to release more energy than our star produces in several days. The signal came from billions of light years away, then vanished. It was not a glitch. Since then, radio telescopes have caught hundreds of similar events. Scientists call them fast radio bursts. Most flash once and are never heard again. A few repeat, sending out multiple bursts in strange, sometimes almost rhythmic patterns. No one knows for certain what creates them. These are not gentle whispers. They are more like cosmic hammer blows, violence compressed into milliseconds. Whatever is responsible has to involve conditions so extreme that they strain our understanding. It is a little like hearing a single shout from another continent, loud enough to reach your ears clearly. The force required would tear apart any ordinary throat. Fast radio bursts feel like that. Signals so intense that they seem almost too strong for their own sources to survive. Some fast radio bursts have been traced back to magnetars, which are neutron stars with magnetic fields trillions of times stronger than the one that wraps around Earth. These stellar remnants are the collapsed hearts of massive stars, packed into spheres only a few tens of kilometers across, spinning at astonishing speeds. Their magnetic fields twist and tangle like rubber bands, stretched too far. When those fields snap and rearrange, they can release bursts of energy that ripple through the cosmos. And now and then, one of those ripples washes over our planet as a fast radio burst. But magnetars are not a full answer. The signals show too much variety. Some fast radio bursts repeat according to patterns so steady they feel almost like clockwork. Others appear utterly random, flaring once from some distant corner, and then falling silent forever. Some bursts seem to arise in regions where we do not see any magnetars at all. A few are so powerful that it is difficult to explain them with any known magnetar model. One particular fast radio burst, with a catalog name that includes the numbers 2120, seems to repeat in a cycle. It sends several bursts over roughly 4 days, then falls quiet for about 12 days, then starts again, repeating this restless rhythm with uncanny regularity. It is as if somewhere in the darkness, a cosmic lighthouse turns its beam on and off on a 16-day schedule. The regularity whispers of some reliable mechanism, while the violence of the bursts suggests forces that should be anything but peaceful. In the year 2020, something remarkable happened closer to home. For the first time, astronomers detected a fast radio burst from inside our own galaxy. Because it came from relatively nearby, they could trace it much more precisely, and the source turned out to be a magnetar. Yet the burst was far weaker than the powerful flashes we see from distant galaxies. If this nearby event is typical for magnetars, then the brightest fast radio bursts from far away may require something even more extreme. So the theories multiply. Some researchers imagine black holes tearing neutron stars apart, their final moments releasing a brief, furious burst of radio energy. Others think of neutron stars colliding with one another, smashing together in a way that sends out these millisecond flares. A few allow themselves to wonder whether such bursts could be side effects of advanced technologies, perhaps beams of energy being sent across space by civilizations far older than ours. None of these ideas yet explain all of the observations. Each fits some pieces of the puzzle, and each leaves others scattered on the table. What unsettles many scientists is the growing suspicion that fast radio bursts are not rare. The universe may be filled with them. Thousands might occur every day, scattered across the sky. We only notice the ones that happen to be aimed exactly toward us, like brief shouts that happen to line up with our listening. Imagine a cosmos that is never truly quiet, full of these sharp, hidden cries, most of them directed into regions we will never see. New radio telescopes with wide fields of view and fast response times are being built and tuned to catch more of these events. Each new detection brings details that deepen the mystery. Some bursts show a strong polarization, which means their waves have been twisted as they travel through magnetic fields. Others show almost no polarization at all. Some seem to come from dense clusters of galaxies. Others appear to originate in relatively empty regions, where there is little matter to shape them. Fast radio bursts might end up being a key that unlocks our understanding of magnetars, black holes, and how matter behaves under pressures and densities beyond anything we can recreate on Earth. Or they might turn out to be something altogether different, a phenomenon we have not yet named correctly, still waiting in the data for us to recognize it. Among all these fleeting cosmic cries, one signal from the past still stands out, quiet and stubborn, refusing to fit neatly into any category. On a warm night in mid-August of the year 1977, an observatory in Ohio called the Big Ear Radio Telescope recorded a narrow-band radio signal that lasted for about 72 seconds. It was strong, focused, and seemed to come from the direction of the constellation Sagittarius. Days later, an astronomer named Jerry Amon was reviewing the printout of that observation. He saw a cluster of numbers and letters that marked the intensity of the signal, and surprised by how clearly it stood out from the background, he circled it with a red pen and wrote a single word in the margin: "Wow." The name stuck. The wow signal is not a myth or a rumor. It truly happened. The telescope really did record something unusual that night. What made it strange is that its properties matched, in many ways, what scientists expected a deliberate extraterrestrial transmission might look like. The signal was centered around a frequency of about 1420 megahertz, which corresponds to the natural emission line of hydrogen, the most common element in the universe. Many scientists had suggested that any technologically advanced species might choose this frequency as a sort of universal calling card, a natural channel they could be confident others would recognize. The wow signal was narrowband, meaning the energy was concentrated in a very small range of frequencies. Most natural cosmic processes produce broadband noise, spreading their power over a wide chunk of the spectrum, like static hissing across many channels at once. A narrowband signal is more like hearing a clear tone on a single radio station while all the others remain quiet. That kind of specificity suggests intention, or at least a process very different from the usual chaos of space. The Big Ear telescope used two separate receivers, side by side, to scan the sky as Earth turned. If a real signal in the sky swept across its field of view, both receivers should have had a chance to detect it, one after the other. In the case of the wow signal, only one did. That makes some scientists suspicious. It raises the possibility of an instrumental glitch or a fleeting interference, but it does not rule out a real, external source. The signal might simply have ended before it could pass through the second receiver's field of view. Over the decades since that night, astronomers have pointed telescopes back toward that same patch of sky many dozens of times, listening carefully. they have never heard the signal again. No repeats, no faint echoes, just the usual background. Many explanations have been attempted. Some proposed that comets passing through the region might have produced the signal, but later studies showed that comets do not emit strongly at the hydrogen line frequency in a way that would match the observed strength and shape. Others suggested satellites, aircraft, or other Earth-based interference, but the details of the signal do not fit these possibilities well. In the year 2024, a new natural explanation was put forward. According to this idea, a highly magnetized neutron star, a magnetar, might have fired a burst of radiation through a cold cloud of hydrogen gas. The cloud could have acted like an amplifier, boosting the hydrogen emission into a powerful, laser-like beam of radio waves, a cosmic maser briefly aimed in our direction. This would produce something that looks a bit like the wow signal. But for this to happen, a very specific alignment of the magnetar, the cloud, and Earth would be required, all at just the right moment. The odds of that perfect geometry are difficult to accept. Another suggestion came from astronomer Avi Loeb and his collaborators. They noted that an interstellar object named 3I/Atlas is passing through our solar system, following a trajectory that lines up suspiciously well with the direction from which the wow signal seemed to arrive. It is tempting to imagine that, back in 1977, when this object was far beyond the orbit of our planet, hundreds of times farther from our star than Earth, it might have emitted a brief, focused radio beam that our telescope just happened to catch. It is an intriguing thought, but still only a thought. No one can say for sure. The truth is that the wow signal remains unexplained. It sits like a single bright note in a vast symphony of noise, lonely and unresolved. If it was a message, it opens unsettling questions. Why did it happen only once? Was it a greeting, a stray leak from some distant technology, a warning, or something we do not have the concepts to describe? If someone tried to speak, why have they been silent for nearly half a century? Maybe they are waiting for a reply. Maybe they tried only once and moved on. Maybe whatever sent the signal no longer exists. Or perhaps they are still out there, watching, while we continue to point our dishes at the sky and listen. As if this were not enough, even the stars themselves sometimes refuse to behave as expected. There is one star in particular that seems determined to break every pattern we trust. A little over 1,400 light-years away, a star informally known as Tabby's star has been dimming in ways that make almost no sense. At times, its brightness drops by as much as roughly 22%. By comparison, when a normal planet the size of a giant world like Jupiter crosses in front of its star, it usually blocks less than about 1% of the light. A dimming of more than 20% suggests that something enormous is passing between us and that star, something far larger than any ordinary planet. Years of observations have confirmed that the dimming is real, but when astronomers look at the pattern, they find chaos instead of clarity. When a planet transits its star, the light curve follows a graceful, predictable shape, a smooth dip as the planet moves across the star's face, then a smooth return as it leaves, repeating at regular intervals tied to the orbit. Tabby's star does none of this. Its dips in brightness are uneven and irregular. Sometimes the star loses 15% of its light, sometimes only 5%. Sometimes the dimming lasts a few days, sometimes many weeks. The timing is erratic. There is no simple, repeating schedule. It is like watching someone flick a light switch on and off in a random pattern. You cannot predict when the next flicker will come or how deep the darkness will be. To explain this, One of the first ideas was a vast swarm of comets orbiting the star. Comets shed dust and gas as they travel, leaving wide, hazy trails. If a loose cloud of cometary debris passed between us and the star, it could block light in complex, shifting ways. But such dust should absorb the star's light and re-emit it as infrared radiation. When astronomers looked for this warm glow, they found none. Another suggestion was that a planet around Tabby's star might have been shattered long ago, perhaps by a collision. The fragments could still be orbiting, forming a wide field of rubble that passes in front of the star in a messy, unpredictable procession. Again though, such a debris field should give off extra infrared radiation, warmed by the star's light and by constant collisions. The observations do not show that warmth either. And so, with each ordinary explanation stripped away, astronomers found themselves drifting toward a more unsettling thought, a more disturbing idea, slowly emerging from the remaining possibilities. Some people let their thoughts drift toward a stranger idea. Maybe the flickering of Tabby's star is not natural at all. Perhaps the missing light is caught by an enormous construction, an arrangement of structures built by an advanced civilization to gather energy from their star. Imagine countless giant collectors, like mirrors or panels, slowly orbiting in great swarms. As they pass in front of the star, they would block its light in irregular, shifting ways. Astronomers have a name for such a concept: a Dyson swarm. It is only a thought experiment, but it fits the erratic dimming almost too well. Curious and careful, scientists pointed radio telescopes toward Tabby's star, listening for narrow, focused signals that might hint at technology. They searched for sharp lines in the radio spectrum, the kind that natural processes rarely create. They heard only silence, no repeating beacons, no whisper of artificial transmission, just a star that behaves beautifully wrong. More recent work has turned back to dust, but with a more delicate touch. If the dust grains are extremely fine and spread out in a very particular way, they might block mainly visible light while letting most infrared radiation slip through. That could explain why infrared observations do not see a warm glow from thick dust, even though the star keeps dimming. Yet this idea opens its own questions. Where does such fine dust come from? Why is it arranged so unevenly? What process can throw up clouds large enough to hide more than 1/5 of a star's light and keep doing it in such a restless pattern? Long-term records add another layer to the puzzle. Old images, taken on glass plates more than a century ago, suggest that Tabby's star has been slowly fading over time. In addition to the sudden, irregular plunges in brightness, the star seems to have grown roughly 15% dimmer over the last 100 years or so. It is as if, behind the sharp, surprising dips, there is also a slow, steady eclipse, unfolding on a timescale longer than any human life. Something out there is changing. Something may be gathering around that star, or something within it may be altering in a way we do not yet understand. Astronomers keep watching, adding each new dimming event to their growing collection. Every time a pattern seems to emerge, the star produces a new dip that refuses to match the previous ones. We are witnessing a story in progress from more than 1,400 light-years away. The light reaching us tonight left that star about 14 centuries ago, when the world on Earth was very different. Whatever is causing the dimming has had all those centuries to grow, evolve, or fade since the light we see began its journey. Somewhere out there, in the present of that star, the mystery has moved on to its next chapter. We can only wonder what Tabby's star looks like now, and what story its current light will carry when it finally washes over us in another 1400 years. While that distant enigma plays out, something closer and more massive is quietly dragging our own galaxy through space. The Milky Way is not gliding freely, it is falling. Our galaxy, along with many of its neighbors, is moving at roughly 455 meters per second toward a region of sky astronomers call the zone of avoidance. The name sounds simple, but it hides a deep unease. We are not drifting aimlessly. We are being pulled. Thousands of other galaxies appear to be rushing in the same general direction. Whatever lies ahead exerts a gravity strong enough to bend the paths of entire clusters. Dust and gas in the plane of our own galaxy block much of the view, hiding the source behind thick curtains of starlight and shadow. We can measure the motion, we can follow the flow, but the destination remains veiled. In the 1970s, as astronomers measured the velocities of galaxies around us, they noticed something odd. After correcting for the general expansion of the universe, there was still a large, shared motion left over. Galaxies in our cosmic neighborhood were drifting toward the same patch of sky, not because space itself was stretching there, but because something was pulling them in. They call this mysterious influence the Great Attractor. The region lies roughly a few 100 million light-years away. Between us and it stretches the disk of the Milky Way, crowded with stars, gas clouds, and dark dust that absorb and scatter the light we most need to see. It is like trying to peer through a dense forest toward a mountain you can only feel as a heaviness in the air. You know there is something vast beyond the trees, but its outline is lost in the tangle of branches. Using X-ray observatories and radio telescopes that can pierce some of the obscuring dust, astronomers have slowly stitched together a rough picture. The Great Attractor seems to be a huge concentration of galaxies, a crowded, massive node in the cosmic web. But when they add up the mass of the galaxies they can see, it is not enough. The gravitational pull is too strong. Something else must be adding hidden weight, likely a deep pool of dark matter layered through the region. Even with that, the story does not end there. As maps of galaxy motions improved, researchers realized that the Great Attractor itself appears to be part of an even larger flow pattern. Our galaxy, along with tens of thousands of others, belongs to a vast collection called a supercluster. The one we inhabit has been named Laniakea, a word that evokes immense heaven. It stretches across hundreds of millions of light-years, forming a gigantic basin in the cosmic web. Our Milky Way is like a small current winding within its immense gravity field. Within this basin, galaxies follow complex, curving paths, drawn along filaments and down into deeper wells of mass. And even Laniakea is not still. The entire supercluster is drifting toward a still more distant concentration of galaxies, known as the Shapley concentration, which lies roughly several 100 million light-years beyond the Great Attractor. There, tens of thousands of galaxies gather in a dense knot, adding their gravity to the pool that reaches us across unimaginable distances. So you find yourself nested inside a hierarchy of motions. Your body rests on Earth, which orbits our star. Our star circles the center of the Milky Way. The Milky Way is falling toward the region of the Great Attractor. The Great Attractor and the galaxies around it are moving toward the Shapley concentration. Each motion layers on top of the previous one. You are traveling through space right now, at speeds that defy simple intuition, carried along by currents in an ocean of galaxies. We can trace the flows, we can chart the directions, but we do not yet fully know what waits at the end of these long falls. Will the Milky Way eventually merge with other galaxies in some distant, crowded future? Its stars, mixing into a new shape? Will tidal forces stretch and twist us as we approach deeper wells of gravity? The answers lie millions of years ahead, in a future no human will see. For us, the fall is a quiet fact of existence. We are bound to a journey we did not choose and cannot escape. While some regions of the universe are thick with galaxies, other stretches are almost frighteningly bare. One of the most startling examples is a place called the Boötes Void, named after the constellation in whose direction it lies. It is an enormous bubble of nearly empty space, a hollow in the cosmic web so large that it seems almost unreasonable. In the early 1980s, astronomer Robert Kirshner and his colleagues mapped the distribution of galaxies and stumbled upon this region. Based on the average density of the universe, they expected to find around 2,000 galaxies within that volume. Instead, they found only about 60. The rest were simply absent. The void is real, confirmed by multiple surveys. It is one of the largest known structures of its kind. If the Milky Way were located near the center of the Boötes Void, our view of the universe would be completely different. Early telescopes would have seen almost nothing beyond our own galaxy. For much of our history, we might have believed we were alone in a vast and mostly empty cosmos, because the nearest other galaxies would be so distant and faint that they would remain invisible to our first instruments. You can think of the Boötes Void as a huge hollow bubble in otherwise solid rock. The stone corresponds to regions filled with galaxies. The bubble is a place where, for some reason, almost none formed. Around its edges, galaxies cluster like a rough shell, but inside, there is a wide, echoing quiet. The universe is about 13.8 billion years old. In that time, gravity has had opportunities to pull matter together and build structures. But it is hard to see how gravitational processes alone could have cleared out a region this enormous so completely. There simply has not been enough time for galaxies to be moved so far from a central area, unless something about the initial conditions was unusually extreme. One idea is that smaller voids might have merged over billions of years, just as soap bubbles can join to form a larger, rounder bubble. In that picture, the few galaxies inside the Boötes Void may be survivors, trapped near lines where smaller empty regions came together. Another possibility is that the void reflects natural variations in the early universe. Some regions started with slightly more matter, which gravity quickly pulled into galaxies and clusters. Other regions started with slightly less and became emptier over time, as their meager matter was drawn away by nearby overdense areas. The difficulty is that the Boötes Void seems too large and too empty to be easily explained by ordinary statistical fluctuations. The odds of such a vast hollow forming purely by chance are very low. That has led some thinkers to toy with more speculative ideas. One controversial suggestion is that the void could, in principle, be artificial, the indirect trace of an advanced civilization that has wrapped its stars in energy-gathering shells. If a highly developed species enclosed every star in their galaxies within Dyson spheres or similar structures, those stars would vanish from the visible spectrum. As their influence spread, more and more galaxies would appear to go dark. From a distance, the region might look almost empty. It is a haunting image, but at the moment, it is nothing more than imagination. There is no solid evidence of engineering at that scale. The Boötes Void does not show any unusual patterns that clearly point to intelligence. It is simply, stubbornly empty. The 60 or so galaxies that do exist within its boundaries are themselves strange. On average, they appear brighter than galaxies in more typical environments. as if the few islands in that dark ocean shine more fiercely against the surrounding nothing. No one is entirely sure why. As our telescopes and surveys improved, astronomers realized that voids are not rare exceptions. They are everywhere. Voids of varying sizes make up the majority of the universe's volume, perhaps around 4/5 of it. The matter we see, the galaxies, clusters, and filaments, occupies a relatively thin, lacy network. Between those glowing strands lie vast stretches of almost nothing at all. You live in a cosmos where emptiness is the rule and matter is the embroidery. Galaxies gather along threads and walls that outline enormous bubbles of space with very few stars inside. These patterns stretch across hundreds of millions of light years. When you step back far enough to see the whole design, the universe begins to look like a kind of foam, a delicate, three-dimensional lace of light surrounding pockets of darkness. The architecture of reality is foam. The universe's foamy pattern hides something stranger. Most of that foam is made not of light, but of absence. Close to 80% of the cosmos is taken up by holes, regions where almost nothing lives. Between the delicate threads of galaxies stretch enormous empty spaces called cosmic voids. Inside them, the density of matter can fall to less than 1/10 of the average, and they can span hundreds of millions of light years while holding only a thin sprinkling of galaxies. Taken together, these voids occupy most of space. Galaxy surveys of the large-scale structure confirm this again and again. From far enough away, the universe stops looking smooth and begins to resemble a sponge, with matter pooled along thin filaments that wrap around great hollow bubbles. One of these hollows, the local void, lies near us. It stretches roughly 60 million light-years across, and our own galaxy sits along its edge. Measurements suggest that the Milky Way is moving away from the local void at about 260 meters per second, as though we are being gently pushed out. Voids behave almost like anti-gravity wells. Dense regions full of galaxies pull matter toward them. Voids, containing so little matter that their gravity is feeble, are slowly drained by their surroundings. Over time, their insides grow emptier, while the walls around them thicken. In the young universe, some regions started slightly less dense than others. As time passed, denser areas pulled harder, stealing matter from their thinner neighbors in a process sometimes called gravitational evacuation. On small scales, this works well, but the largest voids we see are so vast that they strain this picture. Since the Big Bang, there may not have been enough time for gravity alone to carve out such enormous hollows, especially while the expansion of space is trying to smooth out extremes rather than sharpen them. One bold idea is the KBC void, a proposed underdense region so large it might enclose our entire local collection of galaxies, spanning perhaps between 1 and 2 billion light-years. If it is real, we would be living deep inside a cosmic bubble of relative emptiness, and some of our measurements of the universe's expansion could be quietly biased by our special position. Another enormous hollow, the Eridanus supervoid, lies roughly 3 billion light-years away and may stretch from about 500 million to perhaps 1 billion light-years across. It sits in a direction that leads to another puzzle, a strange cold patch in the oldest light we can see. When astronomers mapped the cosmic microwave background, the faint afterglow of the Big Bang, they found a region that appears cooler than its surroundings. On average, it is about 70 microkelvin colder, and in some spots, the difference approaches 140 microkelvin, spread over roughly 5 degrees of sky, and confirmed by satellites such as WMAP and Planck. This cold spot is undeniably real. Small, hot, and cold patches in the cosmic microwave background are expected, but they follow statistical rules. The cold spot is both too large and too cold. By some estimates, the chance of such a feature arising by random fluctuation is less than 1%. It is like shuffling a deck of cards and finding every suit and rank in perfect order. Possible, but so unlikely that your mind reaches for other explanations. One idea is that the Eridanus supervoid is partly responsible. As cosmic microwave background photons cross this low-density region, they would have lost a little energy through the integrated Sachs-Wolf effect, making that patch of the sky appear cooler. Dark matter maps do show an underdensity there, but calculations suggest the supervoid can explain only about 1/3 of the temperature drop. The remaining cooling still calls for something more. Some models look closer to home, suggesting that radiation from nearby galaxy groups might interact with the background light to create an apparent cold patch. This possibility remains debated. The most unsettling idea reaches beyond our universe entirely. In some versions of inflation theory, our observable cosmos is one bubble among many. If, in the earliest moments, another bubble universe brushed against ours, it might have left a scar in the cosmic microwave background. The cold spot has been suggested as such a bruise, a faint memory of contact with something beyond our horizon. Proving that is another matter. How do you test for another universe when it lies outside what we can observe? Some researchers think the cold spot is simply a rare but natural fluctuation, the kind that will arise if you look at enough sky. Others believe the physics of the early universe is more complicated than our current models, and that unknown processes in those first instants may have carved this feature into the afterglow. For more than 2 decades, the cold spot has refused to give a final answer. Whatever its origin, it hints that there is more to our cosmic story than we have yet written down. While we puzzle over scars in ancient light, the present-day universe holds its own quieter terrors. Out in the dark between the stars, countless frozen worlds drift alone. These are rogue planets, worlds that belong to no star. Some were born in ordinary planetary systems, and later flung away by gravitational scuffles with their neighbors. Others may have been torn loose during close brushes between young stars. Now they wander the spaces between, without sunrise or sunset, because rogue planets do not shine. They are almost invisible. We glimpse them indirectly through gravitational microlensing. When a rogue planet passes in front of a distant star, its gravity bends and focuses the starlight for a brief time, making the star appear to brighten and then fade. From these rare events, astronomers can estimate how many such lonely worlds might exist. The numbers are staggering. There may be as many rogue planets in the Milky Way as there are stars, perhaps even more. Billions, maybe trillions, of worlds drift through the dark. Some are giant balls of gas, larger than Jupiter. Others are rocky, Earth-sized or smaller, with solid surfaces locked in endless night. Without the warmth of a nearby star, their exteriors would be unimaginably cold, their skies forever black. You can imagine a city in a permanent blackout, its windows unlit, its streets silent. Then take even the faint glow of distant lamps away and stretch that stillness over billions of years. That is the life of a typical rogue planet. Yet warmth may still hide beneath the ice. Some rogue planets may carry moons. As planet and moon tug on each other, tidal forces flex their interiors, generating heat through friction. Deep below a frozen crust, whole oceans of liquid water might slosh and swirl, warmed not by sunlight but by slow internal fire. On Earth, far below the reach of daylight, life flourishes around hydrothermal vents on the ocean floor. There, chemical energy and heat from the planet's interior support rich ecosystems in total darkness. It is not impossible to imagine similar pockets of life in buried seas on rogue worlds, completely cut off from the stars. If any intelligent beings ever arose in such a place, their picture of reality would be almost unimaginable to us. They might know only a black sky, an endless absence above their heads. Telescopes pointed outward would see little or nothing, because there would be no nearby sun, no bright moon, no obvious galaxies. They could live and die believing the universe contained only their own dim world and the invisible sea of space around it, never suspecting the crowded, luminous cosmos that lies just beyond their reach. Some recent studies hint that not all wandering worlds are cold and dead. Some rogue planets may be even larger than Jupiter, so massive that their own weight slowly squeezes them from within. This gentle, relentless contraction can generate heat, enough for these failed stars to glow faintly in infrared, like embers buried under deep ash. In the endless winter of interstellar space, each would form a tiny pocket of warmth, a small lantern floating in the dark. Astronomers estimate that a rogue planet drifts within a few light years of Earth, roughly every 1,000 years or so. They pass quietly through our neighborhood, common, yet almost totally unseen. We detect them only when chance lines them up between us and some distant star, letting their gravity briefly bend and brighten the background light. The nearest rogue world could be closer than the nearest star, hiding in the far reaches of our own system, moving with glacial slowness through the outer dark. Such a visitor would be nearly impossible to notice. Its gravity would be too weak and too distant to disturb the known planets in any obvious way. Its surface, if it has one, would be far too cold to shine brightly. No reflected sunlight, no glowing atmosphere, just a dark intruder slipping silently through our cosmic backyard. Some rogue planets are ejected at such high speeds that even their galaxies cannot hold them. They will drift out into the more empty space between galaxies, wandering for the rest of cosmic time. These may be among the most isolated objects in existence, forever separated from any bright, nearby companion. All of this makes the universe feel even darker than we once imagined. Between every visible star, there may be dozens of invisible worlds, a hidden population forming a kind of shadow cosmos layered beneath the one we see. If there are so many planets, it is natural to ask a quiet, persistent question. Why have we not heard from anyone living on them? Where is everybody? Our galaxy alone likely contains on the order of 200 billion stars. We now know that many of those stars host planets. Observations suggest that billions of those worlds orbit in so-called habitable zones, where liquid water could exist on a surface or beneath a crust. If only a tiny fraction of those planets develop life, and only a tiny fraction of those evolving biospheres produce intelligence and technology, then simple statistics seem to whisper that there should be many advanced civilizations scattered through the Milky Way. The raw ingredients of life are common. Organic molecules turn up in interstellar clouds, on comets, and in meteorites. The universe has had about 13.8 billion years to roll its cosmic dice. There has been plenty of time for minds to arise, flourish, and look outward. And yet, with all our listening and searching, we have detected no clear signals, no engineered beacons, no unambiguous probes, no vast energy structures wrapped around stars. The silence is so thorough that it feels like a mystery in its own right. Physicist Enrico Fermi captured that unease in a simple question asked over lunch. If aliens exist, where are they? That question has become known as the Fermi paradox. It is like standing in the center of a massive city, knowing millions of people should be nearby, yet hearing no footfalls, no engines, no music, no voices at all, only wind and your own breathing. There are many possible answers, and none of them are comfortable. One is that life itself is rare. Maybe Earth is an extraordinary accident, the result of a chain of events so delicate and improbable that it happens only once in a galaxy, or perhaps even more rarely. In that case, we might truly be alone, or nearly so, drifting through a universe rich in chemistry but poor in biology. Another possibility is that life is common, but technological civilizations are fragile. Perhaps every species that learns to harness energy on a large scale eventually develops tools capable of its own extinction. The window between inventing radio and destroying oneself could be very short. If that is true, the galaxy might be full of ruins and ghosts, the traces of societies that burned bright for a moment and then went dark. A third idea is that advanced civilizations exist but choose not to speak. They might remain deliberately silent, listening but not broadcasting. They may have reasons to avoid announcing their presence, perhaps because they know something about the universe that we do not yet understand. One image sometimes used is that of a dark forest, where every creature moves quietly and hides its light, knowing that any sound may attract hunters. In such a cosmos, broadcasting your location could be dangerous. Survival might require silence. Another sobering thought is that highly advanced beings could be so far beyond us that they simply do not notice a young species like ours. They might operate on timescales and energy scales that make our entire civilization feel like a brief flicker. We could be like small microbes on a rock, living our whole dramas unseen by the giant that occasionally walks past. Then there is the idea of the Great Filter. It suggests that somewhere along the path, from lifeless chemistry to widespread, star-faring civilizations, there is a barrier that is extremely hard to cross. The filter might lie in the origin of life itself, in the leap from simple cells to complex multicellular organisms, in the emergence of intelligence, or in the challenge of surviving powerful technologies. If the Great Filter is behind us, then we are rare survivors of an almost impossible climb. If it lies ahead, then we may be approaching a wall that few, if any, civilizations ever pass. Some studies hint that technological societies might, on average, last only a few thousand years before collapsing or changing in ways that make them invisible to our kind of search. Our own use of radio has been going on for only about 1 century and a bit more. On cosmic timescales, that is less than a blink. Perhaps civilizations are like candles in a dark hall. They flare up for a brief time, casting local light, then gutter and fade, leaving only faint traces in the air. For more than 60 years, we have searched the sky for artificial radio signals. So far, nothing conclusive has emerged. The WOW signal remains our closest brush with what might have been a deliberate transmission, and it came only once, then never again. You live on a world thick with life, circling a star that is one among billions, in a galaxy that itself is one galaxy among trillions. Pure logic says neighbors should be out there. Observation, so far, says otherwise. The silence suggests that something in our expectations may be deeply wrong. Either we are far more alone than we assumed, or something stops most civilizations from surviving and spreading long enough to meet each other. Both possibilities are unsettling in their own ways. While we listen for voices that never quite arrive, we have found other things that challenge what we thought we knew. One of the most troubling puzzles lies in the hearts of galaxies. Deep in the center of almost every massive galaxy, including our own, there lurks a supermassive black hole, a gravitational monster holding millions to billions of times the mass of our star in a volume smaller than the solar system. These black holes are not theoretical curiosities. Their presence is confirmed by watching stars whip around invisible points at incredible speeds, and by images showing the dark silhouette of their event horizons outlined against glowing gas. Their gravity is so intense that once something crosses the event horizon, not even light can escape. Stars that wander too close can be torn apart, their contents stretched and heated as they spiral inward. The question that troubles astronomers is not whether these giants exist, but how they appeared so quickly. When we peered deep into space, we look back in time. Some of the most distant galaxies we have observed are seen as they were when the universe was less than 1 billion years old. Yet many of those young galaxies already host fully grown supermassive black holes at their centers. The monsters were in place remarkably early. It is like walking through a landscape only 1 year after a forest fire and finding a towering, ancient-looking tree, thick and high, as if it had grown for centuries. There has not been enough time for the seed to sprout, grow, and reach that size by the usual rules, and yet, there it stands. Ordinary stellar black holes are born when very massive stars die. If a star perhaps 20 times heavier than our Sun exhausts its nuclear fuel, its core can collapse under its own gravity. If the core is heavy enough, nothing can halt the collapse, and it becomes a black hole with a mass perhaps 10 to 100 times that of our star. Over time, such a black hole can grow by feeding on gas, dust, and the occasional unlucky star. But there is a limit to how quickly a black hole can eat. As matter falls in, it heats up and emits radiation. That radiation pushes on surrounding material, creating a kind of outward pressure that can slow further infall. This sets an approximate maximum growth rate, starting from a black hole with a mass of, say, 100 suns, and growing at that maximum allowed rate. It would take on the order of billions of years to reach the millions or billions of solar masses we see in supermassive black holes. The trouble is that the early universe did not have billions of years to spare before those giants appeared. At the times we see them shining, perhaps only 800 million years or so had passed since the Big Bang. By the usual math, there is not enough time. To ease this tension, some researchers propose that the seeds of supermassive black holes were not ordinary stellar remnants at all. Instead, they might have formed when enormous clouds of gas in the early universe collapsed directly into black holes, skipping the star phase entirely. Such direct collapse black holes could start their lives already thousands or even hundreds of thousands of times as massive as the Sun, giving them a head start. But for such a direct collapse to happen, the conditions must be very special. The gas needs to be extremely pristine, made almost entirely of hydrogen and helium, with very few heavier elements. Heavy elements allow gas to cool and fragment into smaller clumps that form normal stars. Preventing that fragmentation requires unusual environments that may have been rare even in those early times. Another idea reaches all the way back to the first fraction of a second after the Big Bang. In that newborn universe, density could have fluctuated wildly on tiny scales. In some patches, perhaps matter briefly clumped so thickly that black holes formed immediately, without any stars involved. These primordial black holes, if they exist, might have served as the original seeds for supermassive black holes, giving them a huge advantage from the beginning. Recent observations have added more complication. Some growing black holes in the early universe appear to have gained mass even faster than our standard theoretical growth limit would allow. They seem to have ignored the usual constraints on how quickly they can feed. That could mean our models of black hole accretion are incomplete, or that other, more exotic processes are involved. We also do not fully understand the intimate connection between supermassive black holes and the galaxies that surround them. Observations show a surprisingly tight relationship between the mass of a galaxy's central black hole and the mass of the galaxy's inner bulge of stars. Somehow, over billions of years, the growth of the black hole and the growth of the galaxy seem to have been coordinated, as if they were in a long, slow conversation, shaping one another's evolution across vast distances. The exact mechanism behind that coordination remains unclear. Winds and jets from the region around the black hole may regulate star formation in the galaxy, while inflows of gas and stars feed the central monster in return. But the details are still being pieced together. You live in gentle orbit around a star that itself orbits the center of the Milky Way. At that center lies our own supermassive black hole, known as Sagittarius A star. It contains roughly 4 million times the mass of our Sun and sits about 26,000 light-years away, a silent anchor deep in the dark heart of our galaxy. If our galaxy is stitched together around a black hole that may have formed too early to exist by our current rules, it whispers something unsettling about those rules themselves. It suggests that the foundations of reality might be more flexible, more surprising than the clean equations in our textbooks. The monsters sitting quietly at galactic centers are not just heavy objects, they are questions, waiting. While those giants hide in the dark hearts of galaxies, something else, vast and strangely graceful, has begun to appear in the wider sky. In radio maps, astronomers have found enormous, almost perfect circles suspended in deep space, each one roughly 1 million light-years across. They do not show up in ordinary images. Through optical telescopes, the regions look unremarkable, sprinkled with distant galaxies. Only in radio waves do these structures reveal themselves. Faint, ring-shaped halos, almost too neat to be real. These odd radio circles, as they are called, have now been confirmed by multiple radio telescopes. They are not glitches or illusions. The circles are truly there. Each one is bigger than most galaxies, with rims that are surprisingly sharp and well-defined. At these scales, nature usually paints with a rough, uneven brush. Turbulent gas, tangled magnetic fields, and random motions tend to blur edges, not draw perfect arcs. The symmetry feels almost eerie. It is a little like walking across a continent and finding a circle carved into the ground so large you can only see part of it at a time. Its curve steady and true no matter where you stand. You would wonder what kind of process could trace something so precise on such a scale. Odd radio circles give astronomers that same shiver of curiosity. Only a handful have been discovered so far, but that is not too surprising. They shine only in radio wavelengths, and our most sensitive wide-field radio surveys are quite recent. It may be that odd radio circles are not exceptionally rare. We have simply just grown eyes sharp enough to see them. At the center of each known circle sits a galaxy. That alignment is almost certainly not an accident. Whatever creates the ring seems to begin in or near that central galaxy, then spread outward until it reaches a size larger than an entire galactic system. Several ideas are on the table. One leading thought is that the circles are the afterglow of enormous explosions, shockwaves expanding through intergalactic gas. Perhaps two supermassive black holes merged in the heart of a galaxy, releasing floods of energy in gravitational waves and radiation. The resulting shock front might sweep outward, compressing gas into a thin shell that glows in radio waves. Seen from a great distance, the edge of that shell would appear as a ring. Another possibility is that these structures are drawn by jets of material fired from the vicinity of a supermassive black hole. Such jets can be narrow and powerful, but if they precess wobbling like a spinning top that is not perfectly balanced, they might spray energy over a wide region. Over millions of years, this could carve out a roughly circular zone of energized gas. A third idea looks to galaxies undergoing intense bursts of star formation. When many massive stars are born at once and then die in close succession as supernovas, their combined outflows can push gas outward on a large scale. After enough time, that pushed material might show up as a radio-bright ring surrounding the galaxy that originally launched it. Each of these pictures explains part of what we see, but none yet fits every detail. Some odd radio circles show more than one ring, like ripples spreading outward on a pond after several stones have been thrown. That suggests multiple episodes or cycles of energy release. The sheer size, the smoothness of the edges, and the rarity of the structures all remain puzzling. By estimating their sizes and how fast the material seems to be expanding, astronomers infer that these circles are millions of years old. Whatever happened to create them was a long ago event, and we are seeing only its fossil remains. The galaxies at their centers are still there in optical light, quietly shining. Whether they were deeply transformed by the event that birthed the circle, or whether they have largely recovered, is still an open question. As new, more sensitive radio arrays come online and begin to survey the sky in detail, more odd radio circles may appear. Each new ring will bring fresh clues and fresh confusion. Why do some show multiple layers, while others have only one? Why are the shapes so consistently round? What determines how far the waves push into the surrounding space? The universe has always been threaded with hidden structures. We simply learn to see them, one wavelength at a time. While those ghostly circles drift at the edge of our perception, the universe sends us another kind of message from its most violent events, not in light, but in motion. Space itself trembles. In the year 2015, sensitive instruments on Earth recorded tiny ripples passing through the planet. They were not sound waves in air or quakes in rock, but waves in space-time itself. Far away, more than 1 billion light-years from here, two black holes, each roughly 30 times as massive as our Sun, had spiraled into one another and merged. In a fraction of a second, they released more energy in gravitational waves than all the stars in the observable universe emit in light over the same moment. This was the first direct detection of gravitational waves, predicted a century earlier by Albert Einstein as a consequence of his general theory of relativity. The detectors known as LIGO and Virgo use lasers bouncing between mirrors separated by kilometers. When a gravitational wave passes, it stretches space in one direction and squeezes it in another, changing the distances between mirrors by less than the width of a proton. Yet even that almost unimaginably small shift is enough for the instruments to notice. You can imagine dropping a stone into a still pond and watching the ripples spread outward. Gravitational waves are like those ripples, but instead of disturbing water, they disturb the geometry of space itself. Almost any moving mass emits them, but only the most extreme events colliding black holes. Smashing neutron stars make waves strong enough to be felt across billions of light-years. Since that first detection, dozens more events have been recorded. Most involve pairs of black holes merging, some with masses that fall into an intermediate range between about 100 and perhaps 1,000 times the mass of the Sun. Black holes of that size are tricky to form in standard ways, and their existence raises questions about how many generations of mergers or other processes might have built them. A few detected signals seem to come from collisions between a black hole and a neutron star. In one case, the gravitational wave pattern ended before astronomers could tell whether the neutron star was torn apart and scattered before being swallowed or slipped whole across the event horizon. What precisely happens to matter at that last boundary remains hidden. In theory, the countless mergers and collisions that have taken place throughout cosmic history should create a faint background hum of gravitational waves, a kind of constant, overlapping chorus. So far, that background has not been clearly heard in the frequencies that ground-based detectors can reach. That absence might mean the universe is quieter than expected in those bands. Or it might mean we are still learning how to separate the subtle signal from the noise. Future observatories, placed in space and tuned to lower frequencies, will be able to listen for events that our current instruments cannot sense. The slow, deep waves from merging supermassive black holes, each millions of times the mass of our star. The behavior of such titanic systems may either confirm our theories or reveal new physics we have not yet imagined. Some speculative models predict that exotic structures left over from the early universe, cosmic strings, or boundaries between regions that went through different phase changes just after the Big Bang, might also emit gravitational waves. If we ever detect such signals, they would give us direct evidence for phenomena that so far exist only in equations, opening a window onto the very first instance of time. Light, for all its usefulness, interacts with matter as it travels. It can be absorbed, scattered, or blocked, its message blurred by clouds of gas and dust. Gravitational waves barely notice matter at all. They pass through entire galaxies as if they were almost empty, bringing us a pristine record of the motion that created them. We have only just begun to learn how to hear this new kind of message. Each fresh detection adds another note to our growing sense of how wild and dynamic the universe truly is. Among the signals and structures we now study, some of the most dramatic come not from distant galaxies, but from our own. High above and below the Milky Way's disk, there are two enormous lobes of high-energy radiation that should not be there, glowing faintly in gamma rays. In the year 2010, astronomers analyzing data from the Fermi Gamma Ray Space Telescope discovered these gigantic features, now called the Fermi bubbles. They extend roughly 25,000 light-years above the galactic plane and another 25,000 light-years below it, forming a vast hourglass shape centered on the core of our galaxy. Their edges are surprisingly sharp, as if outlined with a careful hand. For a long time, these bubbles were hidden in plain sight, concealed behind the brighter, more confusing gamma-ray glow from the rest of the Milky Way. Only when scientists carefully subtracted known sources did the symmetric lobes emerge clearly from the background. The bubbles are real, and they are enormous. The gamma rays tell us that extremely energetic processes occurred in the galactic center not too long ago. It is as though you looked down on a city from above and saw two huge scorch marks stretching out in opposite directions from its heart. The buildings still stand, the streets are still busy, but the marks suggest that something powerful exploded there in the past. The leading idea is that our central black hole, Sagittarius A star, was more active several million years ago than it is today. Perhaps it swallowed a large cloud of gas or suffered a sudden feast of infalling material. As that matter spiraled inward, it would have heated to tremendous temperatures, emitting fierce radiation. Some of the energy might have been funneled into jets, shooting out above and below the galactic plane. Those jets could have blown bubbles into the surrounding gas, creating the structures we now see, while collisions between accelerated particles and ambient material produced the observed gamma rays. Another possibility is that the bubbles were inflated by a kind of nuclear starburst, a period in which many massive stars formed near the galactic center and then exploded in rapid succession as supernovas. The combined outflow from those explosions could drive a powerful wind that pushes gas outward, carving cavities in the halo of the galaxy and filling them with hot, glowing plasma. Recent X-ray observations have revealed finer structures within the Fermi bubbles, smaller arcs and edges nested inside the larger lobes. These may be signs of multiple episodes, as if the galactic center coughed more than once, each burst carving its own layer. Estimates of the bubble's age suggest they may be only a few million years old, a brief moment compared to the more than 13 billion years of the Milky Way's life. In cosmic terms, whatever happened at the center of our galaxy happened almost yesterday. We orbit quietly in the galactic disk at a distance of about 26,000 light-years from the core, far enough that any direct blast would have weakened to a whisper by the time it reached our neighborhood. But the presence of the bubbles reminds us that our galaxy is not a static, serene island. It has moods and outbursts. It can rearrange its own gas and flood enormous volumes of space with energy. Could such an event happen again? Almost certainly, in some form, though probably not on human timescales. If Sagittarius A star were to awaken into a more active phase, it might again launch jets or winds that expand high above and below the plane. The immediate radiation would be strongest near the center, and we are well off to the side. Still, the long-term effects on star formation, gas flows, and the broader environment are uncertain. For now, the Fermi bubbles hang above and below us like faint lanterns in gamma-ray light, scars in the sky that we only recently learned to see. They are reminders that we live in the afterglow of past violence, in a galaxy that still carries the marks of its own wild history, even as it drifts quietly through the dark. For a long time, we did not even know those great glowing scars were there, simply because we were not looking in the right kind of light. It is hard not to wonder what else lies hidden, just beyond the reach of our current eyes. As astronomers began to map the positions of millions of galaxies, a pattern slowly emerged from the dots. Galaxies are not sprinkled randomly through space like sugar on a table. They gather along long, delicate filaments, threading through the cosmos like strands in an enormous web. Where several strands meet, great clusters of galaxies form, heavy knots in the net. Between the threads lie vast empty regions, the voids you have already visited in your thoughts. This pattern, called the cosmic web, is not an illusion. Every large survey of the sky confirms it. The web stretches across distances of billions of light years, and when we trace it out, it almost looks intentional, like something carefully woven rather than chaotically scattered. One of the largest features we have found inside this web is called the Hercules Corona Borealis Great Wall, a titanic filament of galaxies that seems to stretch for about 10 billion light-years from end to end. Light needs roughly 10 billion years to travel across its length. By many of our cosmological rules, structures that large are not supposed to exist. The universe, on average, should only allow coherent patterns up to a few billion light-years before things begin to look the same in every direction. And yet, there this great wall seems to be, calmly spanning a significant fraction of the observable cosmos. You can imagine looking down at a continent from orbit at night. You see glowing dots where cities lie, and lines of light tracing the highways that connect them. Each lamp and each car headlight is the result of some small, local decision, but taken together, they form a pattern that feels almost designed. The cosmic web is like that, Only the lights are galaxies, and the roads are invisible strands of mass and gravity. To check whether this pattern is truly natural, scientists build computer simulations. They begin with the physics they know: gravity, the behavior of dark matter, the expansion of space. They set up a young universe filled with a nearly uniform mist of matter, seeded with tiny initial bumps, and let the simulation run forward in time. Slowly, the matter gathers into filaments and clusters. Voids open. When they compare the results to what we see through telescopes, the match is remarkably good. Gravity, acting on slight initial differences over billions of years, is enough to sketch out the web. The secret lies in the earliest moments after the Big Bang, when quantum fluctuations created regions that were ever so slightly denser or thinner than their surroundings. The differences were tiny, less than 1 part in 100,000. Over time, denser regions pulled more matter toward themselves and grew denser still, while slightly emptier regions lost what little they had. Dense places became the filaments and intersections of the web. Thin places widened into the voids. Dark matter plays the starring role in this story. It makes up most of the mass that shapes the web. Regular matter, the kind that glows and forms stars, simply falls into the gravitational wells that dark matter digs. The bright galaxies you see are beads hanging from an invisible skeleton. In recent years, astronomers have begun to detect thin streams of gas stretching between galaxies along these filaments. A faint, hot medium glowing softly in ultraviolet and X-ray light. These threads are not just abstract curves in a simulation. They are real structures, channels along which matter flows. Galaxies drift along them like boats carried by gentle currents, moving toward dense nodes such as the center of our own supercluster, Laniakea. Our Milky Way is part of one of those flows, sliding along a strand with thousands of other galaxies. The cosmic web shows that the universe has structure on the largest scales we can access. Beyond the horizon of what we can observe, the pattern almost certainly continues. You live on a small planet, circling a modest star, inside a galaxy that is itself a droplet in a long filament of matter woven through a web that spans the visible cosmos. It would be comforting if the web were the strangest thing we found. But when scientists looked even more closely at the universe's oldest light, they noticed something that seems to point straight back at us. The cosmic microwave background, the faint afterglow from the young universe, contains tiny temperature variations across the sky. These variations are relics of the same early density fluctuations that seeded the web. In our standard picture, their large-scale patterns should be oriented randomly, with no special direction picked out. There should be no cosmic north or south, no preferred axis. Yet when researchers analyzed the largest features in that ancient light, they found unexpected alignments. Several of the broad temperature patterns line up with one another. More unsettling still, they also appear to line up, in a rough way, with the plane of our own solar system and with the direction of our motion through space. Multiple satellite missions, using different instruments and methods, have seen the same thing. The alignment is often nicknamed the axis of evil, partly in jest, partly in discomfort, because it seems to threaten the quiet assumption that the universe does not care where we happen to be. This assumption is called the Copernican principle. It says that Earth should not occupy a special or central position in the cosmos. In modern cosmology, it is built into the idea that, on large scales, the universe should look statistically the same in every direction and from every point. If the largest patterns in the cosmic microwave background really are lined up with our local neighborhood, that would be a serious challenge to this principle. Of course, there are gentler explanations. Some scientists argue that if you measure enough different features, some will align by pure chance, and our human minds are very good at noticing patterns, even when they are coincidences. This is called selection bias. We focus on the surprising alignments and ignore the many measurements that show no such connection. Others suspect that the alignment might be an artifact of how we process the data. Before we can study the cosmic microwave background, we have to subtract foreground emissions from our own galaxy and from nearby sources. If this cleaning process is imperfect in a particular way, it might accidentally imprint patterns that mimic a real cosmic feature. The difficulty is that the alignment has persisted through about 2 decades of scrutiny. Independent teams, using different techniques and different satellite datasets, keep finding something similar. If it is a mistake, it has been remarkably hard to erase. A more unsettling possibility is that the alignment is real and hints that our understanding of the universe's large-scale properties is incomplete. Perhaps the cosmos does have a very slight preferred direction, a subtle anisotropy woven into its expansion or initial conditions. That would mean the cosmological principle is only approximately true, and the foundation beneath many of our simplest models would need to be revisited. Some theorists have played with ideas such as a universe that rotates very slowly or has an unusual global shape that might induce a preferred axis. So far, observations place tight limits on any large-scale rotation, and no clear, simple shape has resolved the puzzle. The most imaginative proposals suggest that the alignment could be a kind of imprint from physics beyond our universe, that our cosmos might be part of a larger structure with its own orientation, or one bubble in a multiverse whose interactions leave faint scars. At the moment, these stories are more like thought experiments than solid science. Most researchers still expect that a more ordinary explanation will emerge, perhaps through better data or a deeper understanding of subtle systematics. But for now, the axis of evil sits there, a quiet question mark in the sky, reminding us that even our most basic assumptions may be open to surprise. As if that were not enough, the universe has begun to hint at its hidden contents through a different kind of whisper. Strange X-rays leaking from places where dark matter is thought to gather. In the middle of the second decade of this century, astronomers analyzing X-ray observations of galaxy clusters noticed a faint, unexpected line in the spectrum. At an energy of about 3.5 kilo-electron volts, it did not match any well-known atomic transition. Hot gas, filled with ordinary elements, produces X-rays at many energies, but not exactly there. The feature appeared in data from more than one space telescope and in several clusters where dark matter is believed to be especially dense. That made people sit up. Because the signal seems strongest in regions where dark matter should be thickest, some scientists have wondered whether they might, at last, be seeing a direct hint of dark matter particles decaying or interacting. If dark matter occasionally transforms into lighter particles, it could release energy in the form of X-ray photons at a specific energy. The mysterious emission line would then be like hearing someone's breathing in a dark room, even though you cannot see them, a subtle but telling sign of presence. One of the favored candidates for such behavior is a hypothetical particle called a sterile neutrino. Ordinary neutrinos barely interact with matter. Sterile neutrinos, if they exist, would be even more aloof, feeling only gravity and perhaps one more feeble force. In some models, a sterile neutrino can decay over very long timescales, producing an X-ray photon at precisely the energy observed. In that picture, dark matter would be gently glowing in X-rays everywhere, its feeble radiance most noticeable in places where it is most concentrated. But the story is not simple. Some astronomers argue that the line may arise from ordinary atoms in unusual states that were not properly included in earlier models. Extremely hot gas can produce a forest of lines, and some may have been underestimated. Others note that not all galaxy clusters show the feature. If dark matter is the source, the line should appear in any region with enough dark matter. The inconsistency raises doubts. It is also possible that more than one process contributes. Some of the emission, around 3.5 keV, might indeed come from dark matter decay, while the rest could be produced by rare states of normal ions in hot gas. Separating these contributions is delicate work. The signal is faint. Extracting it requires long observations and careful subtraction of backgrounds. Small, systematic errors or random statistical fluctuations can easily masquerade as something profound. If the line is eventually confirmed as a genuine signature of dark matter, the implications would be enormous. It would mean that dark matter is not just a silent source of gravity, but a real particle or family of particles that we can study directly. It would bridge the gap between cosmic structure and particle physics, giving us a clue about the substance that makes up most of the universe's mass. To chase this possibility, scientists are planning new observations with more sensitive X-ray observatories and combing through archived data from past missions. They are refining their models of hot gas and testing alternative explanations, all while building theoretical frameworks that predict exactly how dark matter should behave if it is indeed responsible. Within the coming years, as instruments improve and data accumulate, this quiet line in the X-ray spectrum may either grow sharper and more convincing, or fade into the background as a misunderstood echo of ordinary matter. For now, it remains a tantalizing hint. Whatever the truth, you are immersed in this mystery. Dark matter flows through your body at every moment, part of the invisible sea you live in. If it does decay, if each particle occasionally releases a tiny burst of energy, then the space around you is filled with an unimaginably faint rain of X-rays, the softest possible glow from a hidden world we are only just beginning to suspect. Those secret X-rays, if they are real, are far too faint and rare to harm you. They pass through without a trace, like the softest rain falling into an endless sea. But they might be the first faint whisper from an invisible universe that has surrounded you all along. As we listen for those whispers, another idea rises, quiet and unsettling. We may already be living inside one of the largest structures we have ever tried to imagine. Some cosmologists suspect that our own galaxy sits inside a vast, underdense region, a bubble perhaps 2 billion light-years wide. The hint comes from how fast space seems to be stretching. When astronomers measure the expansion rate using nearby galaxies, they find one answer. When they use more distant markers, they find another. The local universe appears to be expanding slightly faster than the distant universe suggests it should. This long-standing mismatch has become one of the most persistent puzzles in cosmology. One possible explanation is that we inhabit what is sometimes called the KBC void, named after the scientists who first mapped out the underdensity. When they counted galaxies out to distances of roughly 1 billion light-years, they found fewer than the cosmic average. It is as if we live near the center of an enormous bubble where galaxies are a bit more spread out than usual. You can picture it by imagining yourself in a valley surrounded by mountains. From where you stand, the horizon is framed by nearby slopes. Distances can be deceptive. The shape of the land subtly distorts your sense of how far things are. and how the world is arranged. Living inside a cosmic void would have a similar effect, but on a scale far beyond any landscape. Light from distant supernovas would pass through regions with different densities, and the way we interpret their brightness could be slightly skewed. Our measurements of dark energy, and even the conclusion that the expansion is accelerating as strongly as we think, might be colored by our unusual vantage point. If that is true, some of what we call dark energy could be a mirage of perspective, but this explanation has its own complications. Voids do exist, but sitting close to the center of one as large as the proposed KBC void seems statistically unlikely. Not impossible, just the kind of coincidence that makes scientists frown and look twice. There is also debate about whether the underdensity is really as dramatic as early work suggested. Galaxy surveys do show regions with fewer galaxies, but those might simply be the normal ups and downs of a foamy universe rather than a single coherent bubble. The way we select and count galaxies could be introducing subtle biases. To test the void idea, astronomers look for specific signatures. Light from the cosmic microwave background, for example, should gain or lose a bit of energy as it travels through large underdense regions, leaving a characteristic pattern called the integrated Sachs-Wolf effect. If we live in a huge void, that pattern should show up in a particular way. So far, the evidence is murky. Some analyses hint at support, others do not. Another test involves galaxy motions. If we sit near the center of a large void, galaxies closer to its edges should be moving outward a bit faster than those near the middle. That creates a distinctive velocity pattern. Observations have found hints of such flows in some directions, but not a clean, consistent picture. For now, the question is open. More sensitive surveys are mapping the distribution of galaxies and their motions over ever larger volumes, trying to see whether the underdensity is real, how far it extends, and how strong it truly is. If the KBC void is confirmed, it would rank among the largest structures we know about, pressing the limits of how we think cosmic structure can form, and stirring fresh questions about how much our local environment influences our view of the universe. It might also turn out that voids of that scale are not as rare as we assumed, and that living inside one is not special at all. In a foamy cosmos filled with bubbles and walls, we might simply occupy one hollow among many, our position no more privileged than a tiny air pocket in a sponge. Whatever the answer, the universe does not confine its strangeness to grand scales. Even in our own planetary neighborhood, worlds have gone through transformations so extreme that they feel almost like science fiction. Around 500 to 800 million years ago recent, by cosmic standards, something happened on Venus that reshaped the entire planet. Radar maps from orbiting spacecraft show vast volcanic plains crisscrossed by fractures and ridges, but almost no impact craters older than about 800 million years. It is as if every scar from earlier times was erased. Scientists call this global resurfacing. You can imagine walking into a house where every wall, floor, ceiling, and piece of furniture has been freshly painted. The underlying structure is the same, but none of the original surfaces remain visible. Venus is like that. The planet itself is unchanged in mass and size, but its skin is new. The leading idea is that Venus's crust may have grown thick and rigid, forming a solid shell that did not break into moving plates the way Earth's crust does. On Earth, plate tectonics allows the surface to slowly recycle. Plates dive back into the mantle, new crust forms at spreading ridges, and heat from the interior leaks out steadily over time. Venus appears to lack such plate tectonics. Its crust acts more like a stagnant lid. Heat from the interior builds up under this lid, unable to escape efficiently. Over many millions of years, pressure and temperature rise. Eventually, the stress becomes too much. The crust yields in a catastrophic way. Huge fractures open. Magma pours out across the entire planet. Volcanic eruptions happen not in isolated regions, but everywhere at once. Oceans of lava flood the surface, erasing old craters, old mountains, and old plains beneath a global tide of fire. For a time, Venus might have glowed like a coal in the darkness, its entire face radiating heat. When the eruptions quieted and the lava cooled, the planet was left with a new, younger surface. The atmosphere, already thick with carbon dioxide and clouds of sulfuric acid, trapped heat so effectively that surface temperatures climbed to levels hot enough to melt lead, with pressures at the ground roughly 90 times those on Earth. Some researchers suspect that this kind of catastrophic resurfacing may happen in cycles. Heat accumulates, the crust fails, the planet buries itself in lava, and then the process begins again. If so, Venus might be sitting quietly between disasters, or slowly preparing for another global event millions of years in the future. Or perhaps the main catastrophe happened once, and the planet now releases heat in smaller, scattered bursts. Venus is hard to read. Its dense, reflective clouds block optical views of the surface. Landers that have touched down there have survived only for minutes to a couple of hours before being crushed, cooked, and silenced. Much of what we know comes from radar mapping and careful analysis of the planet's subtle signals. Recent observations hint that Venus may still be geologically active. Some regions seem to show changes when images taken years apart are compared, possible signs of new lava flows or shifting ground. If that is true, then Venus is not a dead world, just a hostile one, still reshaping itself in ways we are only starting to glimpse. Studying Venus teaches us about planetary limits, how hot a surface can become before rock softens and reshapes, how thick a crust can grow before it fails, and what happens when a planet loses the gentler heat release mechanisms that Earth enjoys. It also whispers a warning. Venus and Earth began as siblings, formed from similar materials in the same early disk around the same star. One became a temperate world full of oceans and life. The other became a pressure cooker. Understanding that divergence helps us understand what must be avoided here. While Venus was drowning its surface in lava, another neighbor met a different fate. Mercury, the innermost planet, seems to have lost much of itself. Measurements of Mercury's mass and radius show that an unusually large fraction of the planet is metallic core. Roughly 60% of its volume is taken up by that core, compared to about 10% for Earth. A normal rocky planet of Mercury's size should have a thick mantle of silicate rock wrapped around a smaller metal center. In Mercury's case, most of that mantle is missing. Two main stories have been told to explain this. In the first, long ago, a body perhaps the size of Mars slammed into Mercury. The impact was so violent that it stripped off much of the outer rock, flinging it into space. Some of that material might have fallen into the star, and some might have drifted away. What remained was the denser core, with a thin layer of rock clinging to it, like the inner stone of a fruit left after the flesh is torn away. The second story looks not to a single blow, but to relentless radiation. In its youth, our star likely shone more fiercely in certain wavelengths and produced stronger winds. Mercury, orbiting so close, would have been bathed in intense light and charged particles. Over millions of years, the outer layers of the planet could have been heated enough for lighter materials to vaporize and escape, a process sometimes called preferential vaporization. the more easily evaporated elements and compounds would be carried away, while the heavier metals remained. Data from the Messenger spacecraft, which orbited Mercury from the year 2011 to the year 2015, have given partial support to both scenarios. The surface shows ancient impact scars and hints of a violent history, but its chemistry also reflects high-temperature processing. It is possible that Mercury's story involves both a great collision and long, slow erosion by the star's early fury, a world injured twice, first by impact, then by light. Despite its nearness to the star, Mercury holds its own little surprises. With almost no atmosphere to spread heat, its day side can reach around 800 degrees Fahrenheit, while its night side plunges to about minus 290 degrees Fahrenheit. In deep, permanently shadowed craters near its poles, where sunlight never reaches, instruments have detected bright deposits consistent with water ice. Comets and other icy bodies may have delivered that water long ago, and the cold traps have preserved it ever since. Mercury shows us what can happen when a world lives too close to its star, stripped, scorched, and yet still holding on to pockets of cold and memory. Together with Venus, it reminds us that planetary evolution can be violent and unpredictable. Not every world finds a gentle balance. Some are melted from within, some are peeled from without, and some, like our own, simply thread a narrow path between extremes for a while. Even so, all the violence and wonder scattered through the solar system feels small beside the oldest mystery of all. How did anything begin breathing? How did stillness start moving? How did chemistry learn to dream? Around 4 billion years ago, this world was a restless place. Oceans covered its face, heavy with minerals and drifting organic fragments. Lightning flickered over the waves. Meteorites fell like brief sparks. Heat pulsed through the young crust. Somewhere in that chaos, something quiet and astonishing happened. Molecules began to copy themselves. No eyes watched it, yet the evidence remains, written into ancient stones and the earliest fossils. Life arrived quickly once the planet cooled enough to hold oceans. But how? Even the simplest living cell is a symphony. Its molecules work together in little storms of purpose. Information stored, copied, read, walls forming, energy gathered. None of these parts matter alone. DNA without proteins is silent. Proteins without DNA lack direction. Membranes without metabolism are empty rooms. Everything required everything else. It is like wandering into a desert and finding a fully assembled machine resting on the sand, many pieces all fitting together with no builder in sight. Somehow, the first living systems assembled themselves from drifting chemistry. Experiments have carved small windows into this mystery. The Miller-Urey setup showed that sparks dancing through simple gases can create amino acids. Other experiments have coaxed strands of RNA into copying pieces of themselves. These glimpses are encouraging, but the leap from scattered molecules to something alive remains enormous. No laboratory has taken that final step. Many imagine life emerging near hydrothermal vents, those deep-sea chimneys where mineral-rich water rushes from beneath the crust. Temperature gradients there might coax molecules into complexity. Others picture shallow pools drying and refilling, concentrating ingredients until new chains formed. Clay grains could have offered their surfaces as templates. Another idea drifts farther still. Perhaps life began elsewhere and arrived here on fragments of rock. But that only moves the mystery outward. Even the choices life made are puzzling. It settled on DNA and RNA, astonishingly complex molecules for storing and reading information. It chose 20 amino acids out of many hundreds to build proteins. Why these? Why not others? Maybe they were simply the ones that happened to gather first. Or perhaps they hold special qualities we do not yet understand. All life on this planet uses the same basic toolset. That unity suggests a single origin, a single spark from which every creature descended. You are built from atoms that once drifted in ancient seas, atoms that found companions, formed patterns, and slowly learned to persist generation after generation, until one day they became you. But beneath that story waits another, older question. How did the universe itself begin? 13.8 billion years ago, everything you know, space, time, matter, energy, unfolded from a state so dense and hot it defies the imagination. The universe stretched outward from something smaller than a moment, a beginning we call the Big Bang. We see its traces everywhere. The faint glow of the cosmic microwave background, the abundance of the lightest elements, and the way galaxies drift apart. But what lay before that beginning? The question itself might be flawed. Time may have started with the Big Bang. The word before might have no meaning. It is like asking what lies north of the North Pole, an inquiry that dissolves under its own shape. Yet the mind still struggles. How can everything appear without a cause? We know a world of switches and wires, of causes turning into effects, but the universe seems to break that rule, arriving unbidden. Some physicists look to quantum mechanics for solace. In that tiny, flickering realm, particles appear and vanish without warning. Perhaps the universe is the grandest of these fluctuations, a ripple that did not fade, a moment of energy that refused to collapse. Others imagine the Big Bang not as a beginning, but as a transformation, a cosmos contracting until it could shrink no more, then rebounding outward in a great bounce. In such a story, the universe has no single birth, only cycles, each giving rise to the next. Another idea drifts through theoretical physics like a whisper. Maybe our universe is one bubble in a vast, eternally inflating multiverse. In that strange ocean, new universes blossom constantly. Ours would be only one among countless others. But such ideas sit beyond the edge of what we can test. Whatever happened before the first fractions of a second, the evidence has been erased by the violence of expansion. We cannot see beyond that veil. Some thinkers, including Stephen Hawking, have suggested that asking what came before the Big Bang is meaningless, because time itself curled to a boundary there. No earlier moment exists, not in any way we can describe. And so we are left with questions that feel as ancient as thinking itself. Why is there something rather than nothing? Why do these laws exist and not others? Why does the universe hold together at all? These may be riddles without answers, or answers beyond our reach. Even accepting that the universe began does not tell us what it truly is. For all our searching, for all the light we gather across the ages, we still do not know its ultimate nature. We still do not know what kind of stage all of this plays out on. The universe keeps its outline hidden. When scientists measure the large-scale geometry of space, they find it behaves as if it is very nearly flat. Parallel lines stay parallel. The angles of vast cosmic triangles add up to almost exactly 180 degrees. On the largest scales we can test, space seems to follow ordinary Euclidean rules. Those conclusions come from the patterns in the cosmic microwave background, the fossil light of the young universe. Tiny temperature ripples in that glow act like a ruler, revealing how space bends. So far, the answer is hardly at all. Within the precision of our measurements, the universe is flat. But flat does not have to mean infinite. You can imagine a sheet of paper that stretches forever in every direction. That is one kind of flat infinity. But you can also roll that sheet into a cylinder or shape it so that walking straight eventually brings you back to where you started. Locally, it still feels flat. You can draw ordinary triangles and never find an edge. In higher dimensions than we can easily picture, space itself could be like that. Flat, yet finite, wrapped quietly around on itself. Astronomers have searched for hints of such wrapping. If space curls back, light from one distant galaxy might reach us along several paths, so that we would see copies of the same object in different directions. No convincing duplicates have appeared yet. We do know there is a limit to how far we can see. The observable universe has a horizon, not because space stops there, but because light from beyond a certain distance has not had time to reach us since the Big Bang. That horizon now corresponds to a sphere roughly 93 billion light-years across. Beyond that, space continues in some unknown way, hidden behind time. If space is infinite, galaxies and voids extend without end past our horizon. If it is finite and wrapped, then a straight journey in one direction would eventually bring you home. Some models imagine a three-dimensional donut-like shape where opposite faces connect. Others picture more intricate topologies with matching faces. Each possibility would leave subtle patterns in the microwave background. So far, none has been clearly seen. The near-perfect flatness itself is another quiet puzzle. For the universe to be this close to flat now, it must have been even closer to flat in its earliest moments. Tiny initial curvature would normally grow until space became strongly curved. Instead, we find it balanced, like a coin standing on edge. This is called the flatness problem. The most widely accepted answer is cosmic inflation. In this picture, during the first tiny fraction of a second, the universe expanded at an astonishing rate, stretching space by an enormous factor. Any initial curvature would have been smoothed away, the way blowing up a balloon makes its surface look flatter over small patches. Inflation explains why the cosmos appears flat and uniform, but it also raises new questions. What started it? What stopped it? And why did it end, with conditions so delicately tuned? So you live inside a reality whose shape is unknown. It may stretch forever. It may loop back on itself in ways the mind can barely sketch. And if one universe with these particular properties can exist, it is natural to wonder whether ours is the only one. The word multiverse sounds like fantasy, but it falls out of several serious attempts to understand our universe. Different areas of physics quietly point toward other universes, separate from ours, each with their own stories. One kind grows from inflation itself. In many versions of the theory, inflation does not end everywhere at once. Some regions stop inflating and become bubble universes like ours, while the surrounding space continues to expand and spawn new bubbles. Each bubble has its own space and time, and perhaps its own physical constants. Our Big Bang would be one such bubble. The space between bubbles expands so quickly that no signal can cross from one universe to another. A second kind arises from one interpretation of quantum mechanics, the many worlds view. Quantum equations describe many possible outcomes for every event. In many worlds, all of those outcomes occur, but in separate branches of reality that can no longer interact. The universe does not choose one path. It quietly grows more branches. If you let that picture touch your own life, every decision and every chance event becomes a branching point. In some branches, you turned left instead of right, spoke instead of staying quiet, stayed instead of leaving. Those other versions of you are sealed away, unreachable, yet in the mathematics they are as real as you are now. A third idea emerges from string theory and related attempts to unify physics. These theories often require extra dimensions, curled into tiny shapes. Different ways of curling them produce different effective laws of physics, different particle masses, different forces, different possibilities. The number of such configurations may be unimaginably vast, perhaps something like 10 raised to the power of 500. If they are all realized somewhere, there is a huge landscape of universes, most of them sterile. In many, atoms would not be stable, or stars could never form. Only a small fraction would have conditions gentle enough for complexity. In that landscape, our universe would not be special. It would simply be one of the rare places where observers can arise. We notice its apparent fine-tuning for life, because only in such a place can anyone notice anything at all. This way of thinking is sometimes called the anthropic principle. The multiverse is controversial. Some scientists argue that universes we can never see or touch lie outside the proper reach of science. Others reply that the multiverse is not an extra assumption, but a consequence. If inflation has a certain form, eternal inflation follows. If quantum mechanics is complete, many worlds follows. A few have searched for faint scars that another universe might have left on our own. Patterns in the microwave background that could hint at ancient collisions between bubbles. None has been clearly confirmed. For now, the multiverse remains an open possibility, hovering at the edge of what we can test. If it is real, then everything that can happen according to the laws of physics does happen. Somewhere, sometime, every possible history plays out. Every pattern has a home. Here, in this version, you are one consciousness on one small world, in one quiet branch, following one path through an ocean of possibilities. Other versions of you may walk under other skies, in other universes, carrying their own questions. And across all those worlds and all those lives, the deepest mystery lingers unchanged, that anything exists at all for anyone to wonder about.